Well, good morning. So what we are going to talk about today is to continue our discussion of the foundation and the groundwork necessary for dealing with time when things change with time. So far we've dealt with things that we've been stationary with time, they didn't change at all, but now we are getting to get started on that. We started last time, we started talking about singularity functions, right? Functions. And we started off with our the most basic function, I guess, or the most fundamental function, if you will, which was the unit step function. So I'm going to review it very quickly for you, which was basically what? We showed it as u of t, and it was defined as being 0 for t smaller than 0, and 1 for t greater than or equal 0. Now what happens exactly at 0, there are different conventions, and they lead to different things. If you keep this convention, it would make dealing with Laplace transform more consistent. So later on, when we are dealing with that makes it easier. But again, there are different ways to deal with that. Anyway, so this was the unit step function, and the way it looked as a function of time, it's a very basic function, almost too trivial to think about, but it's very important. So this is the way it looked. So we said, okay, yeah, so it's just 0 goes to 1, stays at 1. So this is our unit step function. Now, with the unit step function, the other thing that we saw is that, of course, you can have shifted versions of that. So, for example, if you had u of, let's say, t minus t1, we saw that it was actually shifted to the point t1. So it's a unit step function starting at t1. Because that's where the transition point is basically when the argument becomes 0. So that's how you find out when this transition is, in general, for this function and other functions. So that's the way you deal with these things and deal with the shifted ones. So then what we did, we said, okay, we also defined this other function, which was the pulse function, right? We defined it as, so this is the pulse function. And the pulse function was essentially, we showed it as p sub capital delta of t. And it was defined as, you could define it different ways. You could define it as being 0 for t smaller than 0, being 1 for t greater than or equal 0 and smaller than 1, and again being back to 0 for t greater than or equal 1, which basically would look like this. So if this is the function of time again, so this is the unit pulse, which has a width of delta and the height of 1, and it's defined this way. You could also, you can define it as two, in terms of two u of t's, right? 2 unit steps. How did we define that? What was it in terms of 2 u of t's? Does anyone remember? Or can redefine it? Yeah, u of t minus u of t minus delta. Right? This was not a unique definition in terms of these things if you wanted to use multiplication, but this was a unique definition in terms of if you want to, if you want to keep it linear, if you want to keep it as a sum of these functions, not as products. Yes?
If it's supposed to be with delta, shouldn't the 1 be for 0, t is 0, delta rather than 1?
I'm sorry, if the, yes, exactly, thank you. So this was an error. This is delta, obviously, and this is delta, not 1. This point is delta, exactly. I miswrote it and misspoke. So yes, this is correct. It has to be delta. This was an error. Thank you. Okay, so now, you had this unit delta, the pulse function, right? Which is basically has a width of delta, and it basically is a pulse. Now, this is a useful function in many different ways. But one thing we did with this, though, we said, okay, let's look at this function and a scaled version of that. Let's say if we scale this function by 1 over delta. So if you look at this function instead, 1 over delta times p sub delta of t. Now, what can you say about this function is that, of course, what this does, as you make delta smaller, the height becomes larger. So instead of the height being 1, the height becomes 1 over delta. And as a result, the area of this function, this new function, we can define it in this way, is going to be what? always. What's the area of this function if I scale it by 1 over delta? What is it? 1, exactly. So this area is going to be 1 independent of the value of delta. And the other thing that you can do is that, okay, well, now that you have this, if you calculate the limit, when you make delta very, very small, so if you make it very narrower and narrower, start making it thinner and thinner, it becomes taller and taller, because this area has to be constant, right? So as you compress it laterally, it grows vertically. So what happens is that the limit of this function, when delta goes to 0, is defined as the Dirac delta, which is another one of our singularity functions, which is very important. Dirac delta, or the impulse. Call this impulse. And we will see it's quite important in the way we define things. An impulse, or Dirac delta, if you define it really as in form of a function, it's kind of funny, right? Because in the sense that it's 0 for all t's that are not 0, and it's undefined, you could say it's infinity, if you want to speak loosely, mathematically, at t equals 0. Technically, it's not even a function. I mean, from a purely mathematical thing. It's a broader class of things. It's called distribution. But it doesn't matter. We will deal with it as a function. So for our purposes, it wouldn't make a difference. So those are some of the things that we covered. So now you can take this, and so there was this relationship. So we had 2 of these functions. So for example, one of the basic properties of this delta was what? That since it was derived from that pulse function, so the impulse, the area under the impulse is also 1. So if you look at the delta integrated over all the times, it is going to be, the area is going to be 1. So the way we show delta usually is that we show it with a thick arrow, with a thicker upward arrow. And when you want to talk about the scale of a delta, it really makes sense to talk about its area. So if I multiply a delta by, let's say, if I take the delta of t and say, what is 2 delta of t? Right? The height is infinity here and 0 at other places. So you can't define it really in terms of its height, right? Because it's already infinity, so it becomes, meaning 2 times infinity, right? Whatever. So you define it in terms of its area. So when the difference between this guy and that guy is that the area of this guy is twice the area of a regular delta. So its area is 2 as opposed to 1. But anyway, so going back to this is also true because now all of this area comes from this very, very thin sliver around 0. Therefore, mathematically speaking, you can also write it this way, which means that going from the left limit of 0 to the right limit of 0, this is also, that integral is also 1. So all of that area comes from this region. So that's fine. And the other thing that we notice is that now if you pay attention to this and evaluate this function, again, I'm going over these fast because we went over them last time. It's just a review for you. It's basically, if you look at this, now instead of integrating from negative infinity to positive infinity, to plus infinity, what if we integrate it from negative infinity to t? What is its value? Well, it depends on t. So integrating this from negative infinity to t means that I start from way out here and start integrating what is the area as I start increasing t. 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, right? So what happens is that if you think about it, it is basically this integral is 0 for t smaller than 0 and 1 for t greater than 0. Which by definition is u of t. So you can see that the integral of delta is u of t. Now, we started with this notation, which we said, as I said last time, which will remain dormant for a couple of lectures, and then eventually will pop up and dominate everything for a little while. And that's this notation of p. So there's this operator p, which is called the Heaviside operator. So operator p is defined as the derivative with respect to time. So just it's a shorthand form for derivative. And this 1 over p, again, it's a note. Think about this entire thing as a symbol for now. There's a reason we write it as 1 over p. We'll see later on. But for now, think about this entire thing as one giant symbol. It makes sense. Later on we'll see, but we haven't proved that yet. I mean, you can think about it in a way. I'll show you how it makes sense even now, but which is not that difficult. So it's the integral from negative infinity to t, dt prime, of some function. You can see they're inverse functions, right? So if you apply them back to back, you can say it's like a product of these operators. They should cancel each other out. That's why we write it this way. And you will see that it's actually quite generalizable. And they behave like rational functions. We will show that, and then we'll use that later on. But again, right now we are not doing any of that. So anyway, so if you take this notation, what this says is that the integral of the delta of t is u of t. Or conversely, delta of t is the derivative of u of t. So you could have actually defined delta of t this way. And we talked about operators, and we'll talk quite a bit more about them. Operators are essentially, what are operators? I mean, what are functions? Functions are these boxes that you put something in, you put a number in, it gives you a number, right? It produces a number for you. You put 2, it gives you 4. You put 1, it gives you 1. You get 3, it gives you 9. You put 0, it gives you 0. So that could, for example, be t squared or x squared, right? But operators are one level higher. Operators are essentially boxes that you throw a function in, and it produces a function. So its input is a function, its output is also a function. Anyway, so these are operators. Anyway, going back to this discussion, so what we saw is that there's a delta and u. So there's this like step function and delta function are related to each other through this relationship. And that's fine, that's nice. Now, there's nothing to tell you that you stop here with the singularity functions, right? What if you integrate, for example, the u of t? What is 1 over p of u of t? What is that? If you think about it graphically, right? What is the integral? Essentially, if you want to think about design, you have to visualize something at some level. And that's why these visual tools are useful to understand. So, okay, this is u of t. What is the integral of this thing? Starting from negative infinity. What's the area? 0, 0, 0, 0, 0, 0, 0, 0, 0. What is it here right at 0? 0, but then what? It starts increasing, right? At the farther I go, the more area I accumulate. So what is the integral of this thing? T, right? So it would look like this, with a slope of 1. This is called the ramp function, unit ramp function, which is defined as, so r of t is defined as 0 for t smaller than 0 and t for t greater than 0. Can you express this in terms of u of t directly? T u of t, right? Exactly. T u of t. So what's the next one up? If you want to think about it. What is it going to be, let's say? It doesn't have a specific name. So the integral of r of t. But what is it? Go ahead. Yes, but how do you describe it? 1/2 t squared, right? Is that correct? Is that complete? Sure. How do you show that? So this is basically what she said. So it says t squared over 2, but then it has to be 0 for t smaller than 0, right? But because if you just plot this quantity, this is not the integral of that, right? This looks like this. This function looks like this. You want something that looks like this. How do you achieve that? Times u of t, right? That's one way to achieve it, right? So if I write it as this times u of t, that would do it. Okay? Make sense? So it's something that suppresses the left half, essentially, right? The left wing is completely suppressed. Say again?
What if you want the left to be something different from the right, but not 0?
So tell me how you do that. So the question is, this is a good question. So say, what if you wanted the left to be something different from the right, but not 0? So how do we do that? So I let you decide. Let you think about it. So how do you get to suppress the right? if you want to suppress the right. This suppresses the left, right? What is the function that suppresses the right? U of negative t, right? So then what do you do with the u of negative t? So let's say I wanted this to be t squared plus over 2 on this half, and I want it to be, I don't know, a cosine on this half. Not, I don't know if it's a particularly useful function, but let's just make it, right? So how would you do that? So you have this is the right half.
Plus cosine times u of negative.
Cosine of t, u of negative t, right? So you can see that actually you can build quite a bit of stuff with this. And let's do that actually now. Now let me just get rid of this, because then people will look at it and say, what is this? It's fine. I mean, there are things that you could try to make something up that would require something like that. But so you have that. That's fine. Now, but it's actually quite powerful. Even these 3 to 4 basic functions that you have are quite powerful in terms of defining and creating or deconstructing functions. So let's say you wanted to create a waveform. I don't know, I'm just making something up here. Let's say you wanted to describe a function that looked like this. Okay, so let's say I'm just making these things up. 1, 2, 4. Let's say this is 1, this is 2. So this function, let's say, this f of t. I want to be able to, would I be able to describe this in terms of those basic singularity functions? Let's construct it together. Let's construct it as a discussion here. So what we are trying to do is basically just to start constructing this together. So f of t, and we'll go around the class and ask you questions. So let's see. This time I'm going to start from somewhere that I haven't started before. Okay, second in the back, second row. Maybe we can go that way. All right. So what is the first function that you would use to start from negative infinity up to here? You don't need anything, right? So what's the first function you would use to start this? R of t. Okay, so R of t or u of t times t. T u of t. That's fine. Let's write it as R of t. That's good. So now, what if we, okay, so, but R of t keeps going, right? So how do you stop it? So now you need to get something here going on that would cancel that beyond this point, right? So let's just draw these functions. Actually, I'm going to color coding. So this is your R of t. Right? I'm going to not show the left side because it's 0 for all of them. So that's your R of t, R of t. So what's next? What would you do to make it flat? What do you need to do?
Minus R of t minus 1.
Exactly, minus R of t minus 1. Because R of t minus 1 is, so let's use a different color. So this is R of t minus 1 shifted by 1, and if it's negative, it becomes like that. So this is minus R of t minus 1. So it gets, so now the function becomes, a new function goes up, becomes flat, keeps going flat. Then what do I need here? So let's move on to the next person. Go ahead. So what do I need to do here? To
subtract R of t, I think, plus 1, but it's like outside of the parentheses.
Okay, so if I plus 1, be careful though,
okay, yeah,
because 1 is a dangerous thing,
right?
1 is a very powerful, potent thing. 1 would bring everything up, 0 and all, negative times, positive times, and all those things, right? So, so first, just make this jump. Let me just propose that. Just make the jump. Don't worry about the slope. Let's just make the jump. How do you make the jump? What gives you a little jump?
U of t.
U of t, right? So go with the u of t here. Right? So plus u of t. Okay, now what? Then next. So go ahead. Oh, okay. So good. You caught me in there, right? So this is not what I drew. U of t is here. This is u of t minus 2. All right, thank you. So now what's next?
now you just subtract r of t?
Yeah.
Or r of t minus 2.
Exactly. So subtract r of t minus 2. So now where are we? So yes. Why is this u of t minus 2? Is that the question? Because think about this green function. Right? That's the function I'm adding. Because these, the blue and the red together give up to here, but then keep going. U of t wants to create, u of t minus 2 is here to make a jump at t equals 2. Because remember, u of t minus 2 is shifted. U of t. You need to shift them in time, right? Yeah, okay, no, but you don't look convinced. You have to be convinced about it. What is u of t? What does u of t look like? Do you agree? That's the way it looks like. What does u of t minus 1 look like? Shifted over by 1, right? What does u of t minus 2 look like? Shifted over by 2, right? That green function you see here, it's this guy. Does it make sense? The reason, all it does is just to produce this jump for us. But then it would stay up there. You're not done yet. So we have to add more stuff. That's why he added the orange r of t minus 2, which is this orange function, negative r of t minus 2. So that basically starts bringing it down. All right? Good? Everyone's good with this? Everyone's okay? All right. So are we done? No, you're not done. Because this looks like this, except for the fact that it will keep going all the way down. You have to stop it. So what do we need? What's the last thing we need to add? Rohan?
R of t plus 4. Or R of t minus 4.
R of t minus 4. So plus R of t minus 4. So let's see if I have another color. Okay. So this guy plus R of t minus 4. Okay? And that would produce it. So now, you say, okay, why did you write it this way? Why do you think we write it this? Why do you think writing them expressing it in this form could be useful? Go ahead. Superposition, right? Right. Yes. So you're not the designated superposition person, but you're okay. That's good. Correct answer. That's fine. Good. No, that's fine. So why superposition? Because once if you have a linear system, and not all systems are linear, but if you have a linear system or it can be reduced to a linear system, then you reduce it to smaller functions, the response to which you know or are easier to determine, and then you can write the overall response as the sum of these responses. And you will see that we will actually take this to the limit pretty soon. And that's basically one of the core concepts of systems in general. But essentially, this is pretty powerful because now you can imagine that you can write all sorts of things, even if you have quadratic or cubic and things of that sort, you can write all of them in those forms. I could also rewrite this in a slightly different form. If I wanted to make everything in terms of u's of t's, I can write as t u of t. Well, I'm just going to be lazy, not switch colors. Minus. So what would this one be, by the way, if I wanted to write it in terms of u of t? So this is something that you need to be careful. I want everyone to think before you answer. What is this one if I wanted to write it in terms of u of t? Is it, okay, what is it? T minus 1 times u of t minus 1, right? Because it's a change of variables. R of t was u of t. So if you change t to t minus 1, you have to do it on both fronts. Which makes sense, right? Because if you make a t u of t, as soon as you start here, you start at 1 or negative 1 since it's a minus sign, right? You won't start at 0. Anyway, plus, so what is this one? T minus 2. Oh, no, this is just u of t. And this one is t minus 2, u of t minus 2, plus t minus 4, u of t minus 4. You could write it this way too, if that makes, because then you can factor all the, well, you can't factor all the u of t's, never mind. So it is what it is, because there are u of different t's. All right, any questions? So if I give you a function of any form or any shape, you can actually deconstruct it or decompose it into these like elementary singularity functions, right? So you're ready to do that? Okay. Okay, so let's keep this here. Any questions so far? No questions? Yes? Okay, so forget about the purple line. If I didn't have the purple function, everything up to the purple, what would it look like? It would look like the brown, except for the fact that at its end, it would keep going, right? It wouldn't become flat. I want it to become flat, become 0, right? It keeps going down, so that purple line comes and counteracts that, so it keeps it flat, cancels that part from that point on. Otherwise, this will keep going, right? Any other questions? No? All right. Okay, now with the really important stuff. So I gave you an example, it was kind of like a contrived example, right? I mean, it has like a piecewise linear function, all those things. What if I give you a general function, an arbitrary function, f of t? Well, let's call it f of tau. Right? No, actually, let's make it f of t. Sorry, never mind. Because I have to decide which way I want to go eventually with this. So f of t. So let's say this is the function f of t. Some arbitrary function. Can you approximate this function with a bunch of, one of those, or a bunch of some of those singularity functions? I would suggest that we do this with the pulse function, p sub delta. So we want to use p sub delta of t. You remember p sub delta, right? It was this guy. 1 and delta, the width of delta. How would you do that? This is similar to the proof we had for the fundamental theorem of calculus, right? So you just basically show it like this. So you can say, all right, Can I write it this way? In other words, think about one of them. Think about just one. Let's say this is tau. Let's say this is time tau. Let's think about this box. Right? What is this value here? F of tau, right? So this is f of tau. So how do you describe this one? How do you describe just this box, if I didn't want to have any of these boxes, in terms of the p delta? How would you write it? What is this box? Anyone? Yeah, go ahead. P of t minus tau, p delta of minus tau, times what? F of tau, right? Because you have to scale it, because the height needs to be adjusted to the height of the function. So you just scale these up and down based on the value of the function, right? So if you look at the f of tau, and you look at that, this is basic, this describes this one box. Does it make sense? So I can put these boxes next to each other and approximate this function. It's an approximation right now. Fair? So I could do it, and I know the width of these pulses are delta, the way I've defined it. So instead of writing tau, I could write basically, let's say this is let's say I break it up into deltas, so I can write it as n times delta. Right? Fair? So I can write this as, this one of them is going to be f of n times delta, p sub delta of t minus n delta. Good? We're good with that? I just write it in this way. So if I want to write all of them, I have to add a whole bunch of them shifted with different values, right? So I can write it as a sum. So this function, f of t, is approximately, because you yeah, it's different here, right? I mean, you can see that there's an error here and here. You're not mapping it exactly, at least not yet, right? So that's going to be the sum of these things for different values of n. So I'm putting multiple boxes next to each other with different heights. N equals negative infinity to positive infinity, right? So if I want to cover my function all the way from negative infinity to positive infinity, that should do it. Fair? Good? Now what is this? If you think about these values, it's kind of like a lookup table, right? You've turned the function into the value of its samples. You say, okay, well, you know, I know what the function value here. So I could basically give you a table, say, well, a table, say, well, t and f of t, right? I can say 0 is like, I don't know, 1. 1, 3.5. 2, 4.37, etc., 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 right? So I can give you a lookup table of values, of numbers. These are the values. That's the lookup table. I look at the values of the function at any point at the beginning of this pulse and use that to control the height of the pulse and approximate the function with that value, that constant value, over that time period. Right? It's an approximation, right? But there's nothing wrong with it. So now let's do something a little bit. Let's make a tiny modification to this. So let's write the same sum of f of n delta. Now what I will do, I divide and multiply by delta. Right? Now think about this. Or before you even think about that, what would you do to make this more accurate? If you wanted to make this a more accurate representation of the function, what would you do? Make delta small. The smaller you make delta, the more accurate this becomes. And do you agree that in the limit of delta going to 0, this represents the function exactly? Unless your function is really not doing some crazy stuff. You can still make functions. I mean, I can make really bad functions that you can't do this with. But those well-behaved, mostly continuous or more or less well-behaved functions. You can represent them this way, right? So what would I need to do to make this accurate, to make this exact? What do I need to do? So to get that exact f of t, do you agree that, if it's a well-behaved function, the limit of delta going to 0 of that would determine this, right? So it would be the limit of, okay, so now I'm running a little bit out of space here. What's the best? Okay, you know what? Let's do it here. F of t is going to be exactly this, subject to well-behaving functions, or for well-behaving functions, rather. F of n delta, 1 over delta p sub delta of t minus n delta times delta. Now, what is this in the limit? You can actually bring the limit inside the sum. What is the limit of this guy? Delta of t minus what? So let's define this n delta. So n is going through all values from negative infinity to positive infinity. So you're stepping it through small steps. So it's actually the instantaneous value. Let's call it tau. Let's call this tau. If we call that tau, then this becomes what? What is this function in the limit? Dirac delta of t minus tau. And what does this become? Right? So this basically is, there's another notation for this sum, which we did last time. F of tau, delta of t minus tau, d tau. We derived this in a different way. We called it the sifting property, right? But this is what it means. Now, what does this mean now, really? This is important. This is the part that you need to really pay attention. Because if you understand this, everything makes sense a lot easier for you. This is nothing but that lookup table. This is a continuous lookup table. These are values of the function. This is the part that's a function of time. This is the only part that's a function of that time t. So you have actually decomposed your signal. You've expressed it in the, so now I'm going to speak a little bit mathematically, but you know what it means now. This is a basis for all functions. The deltas at different times form a basis. So you can write any function as this sum of all these deltas, because which basically is a limit of all these pulses, which kind of a trivial basis, right? You say, I can show any function by knowing its values exactly at any point in time and put that value exactly where it is, it has that value, and then putting all of them together. If it sounds trivial to you, that's good. Because I could say it 5 different ways that wouldn't make it trivial. The point is to make it trivial to you. Yes?
Isn't f of tau essentially the same as f of t, is just tau instead of t?
Sure, but it's the summation that's happening on that, right? This is basically where the summation is happening. That you need to have a different variables, right? This is the one where you're doing the summation or integration, essentially. That's why tau is the variable of integration, right? This is the step size, d tau. This is n delta tau. And then this is just basically tau. I mean, so this is this is tau. N delta is tau, and this is tau. That's the stepping function. That's basically where you summation part. So you write it as a sum of all these pulses, essentially. But the limit for a continuous function is the sum of these impulses. So when you see this, think this. Even better, think this. Then it makes sense. Any questions? Yes?
So basically, if I interpret this correctly, if I just took any point tau equals to, I don't know, t naught, then because it's the Dirac delta function, then it's only at that t naught, that f of t naught that matters.
Correct.
So everything else just kind of cancels out, and that's why we can express the function in this way.
Right. So what you're saying is that since the delta of t minus tau is non-zero only when t equals tau, this basically takes the value of function at t equals tau and takes it out. And that's why f of t is that. That's correct. That's an exact correct. And that's why it's called sifting property. You sift it out. You just take that value out. Exactly right. But it also does more. I mean, that was the way we thought about it last time, right? We didn't do it this way. We did it in a different way. But this time we are doing it this way because it allows you to think about this. Really, what the thing that has a functionality of the time is this. And you will see in a second why this is very, 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 very important. Any other questions? This should be crystal clear in your minds. Any questions? Yes?
I still don't follow why tau isn't t.
Why tau isn't t? But, okay. So let me ask you this question. So think about this axis. This axis is t. When I'm adding these pulses next to each other, think about the discrete case. Each one of them is a function, right? Each one of them, let's say this guy, is that. This function, if I were to plot this function by itself, it would look like this. Right? So now I'm making this out of a whole bunch of these functions that are 0 at all times except for these like little short intervals. That's the sum. Now, this summation is done over the parameter of this. I need to move this up. That's this n. This n moves this pulse across. Right? So that's when the summation is happening. So when I go from summation to integration, this is the one that I'm integrating over. This is the variable I'm changing along. Now, t is an arbitrary function. So, well, I am interested in value of this at t equals whatever, 45 seconds. Right? So that has no impact on this summation. If I fix it, then no summation will occur. If this were t, no summation will happen. Right? Any other questions? As I said, this should be crystal clear. Good? No? You tentatively look like you have a question, but you're not sure. Okay, all right. Sorry. All right, so where are we going with this? Now let's start thinking about, so we are going to start thinking about one-sided functions. Now, one-sided things are, you've seen a lot of one-sided things, and once we saw one-sided functions, u of t is one-sided. So what do we mean by one-sided? So one-sided functions are essentially, so one-sided functions are those whose value, f of t, is 0 for all t smaller than 0, like u of t, like r of t, right? Essentially, what you're assuming is that there is some beginning to things happening, right? You can say, well, what happens before that? So, well, if you're really concerned about what happens before that, move your time to define your t equals 0 at that point. So how about before that? So I'll move it there. Well, move it to Big Bang, t equals 0. So what about before Big Bang? That's a meaningless question. Why is it meaningless? Because time, time is implicit. I mean, the only way you can define time is in the context of change. If you have no change, there's no way to define time. Right? So in the absence of change, there is no time definition. If nothing changes, you can't define time. And the other thing is that there's also another assumption here for this thing, which is important because this comes into what we call causality. Causality means that the response of a system, so if you think about a system and its response cannot precede its input. In other words, the input will cause the output. So if you start with an input that's one-sided, the output has to be one-sided. Right? Because if you have output before you have input, that violates causality. But there's also something that's even more fundamental to causality. What is more fundamental to causality? It's the assumption of monotonic time and one-directional time. Again, we see this on a regular basis in our daily lives because we just take them, assume that these are completely, these are laws of nature. And they may be laws of nature, but, we just are looking at it based on a very limited subset of things. If you don't have linear time, or not linear, monotonic time, and if you don't have unidirectional time, causality doesn't mean anything. And that's one of the challenges with proving things with causality. Say, well, what caused all of these things? Well, what do you mean? Causality has time implicit in it. And if there's no time before a certain event, then we can't talk about what caused it. Anyway, so going back to this stuff. So we start with one-sided functions. And what we are more interested in, so I'm going to erase this, is a system, which really you can think about in different ways. So this is the system. Now, a system has an input and an output. So let's say you have an input of x of t and an output of y of t, meaning that if you put something into it, something else comes out. You can think about it as a box that has an input, like you put some waveforms in and a waveform comes out. You could think about it as a mechanical system. You kick it, it does something. You can think about it as an acoustic system. Some sound comes in and does something to the sound, right? I mean, this room, for example. You can think about everything. You can think about it as a financial system. People start buying and selling things, putting money into market or taking money out of it, and it responds to it. The price of a stock goes up and down. There are essentially unlimited number of things that can be viewed this way. What it really is an operator. Another way to think about it is an operator. So you have this operator, H, that's defining system, which operates on the input and produces the output. So what it really does, you can show it also this way. Produces y of t. Right? So what do I mean in a practical sense is that, for example, if this is x of t, if x of t is something, then y of t is something else. for example. This is a very simplistic one. You put something in, it produces something at the output. So it takes a function, it produces a function, if you think about mathematically. If you want to about physically, it's something has an input. When you do something to the input, something happens at the output. Either way, the key point to this thing is that now you have a decomposition for your system, for your input. So this is the key part. So remember, we could write any function in terms of the deltas, express them in terms of deltas. So if I can do this, I can write as x of tau, delta of t minus tau, d tau, from negative infinity to positive infinity. Right? So that's x of t. Do you agree that this is a valid thing? We just wrote the same thing with f. Just change the name of the variable. And what is this? It's a lookup table, a continuous lookup table of values of x and functions of t that are deltas. Now let's see what the system does to this, what the operator does. So I'm trying to find out what the output, y of t, would be. Right? So y of t is h operating on x of t, which would be h operating on that expansion in the basis of deltas. Now, if I have a linear system, this is a bunch of little inputs, right? I can evaluate the response to this as individual responses to individual inputs, correct? Which is also known as superposition, yes. All right, good. So then this guy takes functions of time and produces functions of time. And if this is a linear system, it doesn't care about scaling. It doesn't care about a number 3 or 4 or 5.3 being in front of it. A scalar scaling in front of it wouldn't affect anything, right? So it's completely impervious to these guys. These are just numbers. This is the lookup table, remember? I hope I have indoctrinated you in this way of thinking already. So anyway, so this is the lookup table, right? So this doesn't do anything to this guy. So it goes all the way through. The only thing says, functions of t. I have business with these guys. I don't care about the rest of them. I have to deal with these. So what does it do? Then I take the integral. It goes through the integral. It's oblivious to the rest of it. And then it goes through. OK, well, no, I found something that's a function of t. Now I have business. So what does it do? What does it do to this thing? What is this, if you think about it? What is that? Not mathematically, physically, what is it? What does it represent? This is the operator that represents the system, right? It represents its response to something. What is that something? What is it? Delta of t minus tau, right? So it represents the response of the system when the input is a delta at time t equal tau. So this is delta of t minus tau. It's the response of the system to an impulse at time t equal tau, right? That's what that operator does. So we show that as, so the assumption here, so we made an assumption of linearity. Now, so negative infinity to positive infinity of x of tau. Now this thing, I show it with lowercase h sub t of tau. It's the response of the system to an impulse at time t equals tau. So this is delta of t minus tau. And this is h sub, this is now going to be h sub t of tau, or tau of t, doesn't matter. This is the response of the system. impulse response of the system to an impulse at time t equal tau. You can see it's both function of t and tau in general. So you can also write it this way, which is what I think is a preferable way of showing it. It's a function of two variables, t and tau. It's the impulse response of the system at that time. It means that if you hit it with an impulse at this point, it would do something. So this is that h sub t of tau. No, this is not. This is tau. And this is h sub t of tau, or t. Let's say just this is h of t and tau. Make your life easier. Now, in general, if your system is time varying, these impulses could be different. So if I hit it with a different impulse at a different time, if I hit it here, well, just a different color, if I were to hit it with an impulse here, it may do something else. Right? Because it depends if the system changes with time. In general, it has to be function of t and tau. That's why it's function of two variables. This is another way to think about it. This is a catalog of impulse responses. So you say, well, yeah, the impulse response for this time looks like that. For this time, it looks like that. This time looks like that. It's a function of two variables. It defines a surface, right? If you have an xy, then on the z plane, it shows a surface. That changes. Now, that's fine. But if the system now also becomes time invariant, so we made one assumption, linearity. But now we also assume that the system is time invariant. Time invariant, meaning it doesn't change with time. Its properties do not change. Not that it's static. Doesn't mean it's static. It means that its properties that don't change with time. Its behavior today and tomorrow are the same. Right? Then this becomes x of t, h of t minus tau d tau. Now the impulse response would only depend on, this should be, okay, delta of t minus. Then the impulse response would depend for a time invariant system would become h of t minus tau. It would only depend on the difference of the times. In other words, if you hit it at time t equals 0 with an impulse, so if this is delta of t, its output, so this is system H, its output going to be something, some h of t. Now, and this is that h of t shifted by tau. Now, these are very important results. This is called the superposition integral. Some people incorrectly call this the convolution integral. This is not the convolution. Superposition integral. Some people like to call it time-varying convolution. Okay, I'll let them do that. But more accurately, superposition. This is called the convolution integral because it defines a very important operation, extremely important operation between two functions, the x and h. Now you can easily see that if you also do a change of variable, if you define t minus tau as t prime or tau prime, then you can see that you can also write it in this form. X of t minus tau, h of tau, or let's write it this way, h of tau, x of t minus tau, d tau, with the change of variable, right? So this is a change of variable. But the point of this is that you can see that it commutates the operator. So the convolution of x and h is the same as h and x. So basically there's a shorthand notation for it. So you can show x asterisk h, which is equal to h asterisk x. Now you probably don't have any intuition about this yet. And one of the things we'll do is to develop some intuition about it, what this is. And it's a very useful thing to develop intuition about. So you don't have it yet? That's fine. Yes?
What if you change from going from
What did I change? I assumed it's time invariant. This is the assumption. I usually write my assumptions over the equality signs. Say what allowed me to go from here to this. So here I assume linearity. It allowed me to bring this operator inside the integral and operate on this. Here I assume it's time invariant. And what it did, it allowed me to take this function of 2 variable and take it into use a function of 1 variable. Meaning that the impulse response doesn't change with time. Now you may say, why, if the impulse response doesn't change with time, when we say it doesn't change with time, we have to be careful. This is also another thing, pay attention to this one. So then why isn't it just a function of t or tau? Why is it a function of t minus tau if it doesn't change with time? Think about this. Think about this as a system, this whatever, table. If I kick it now, and it says goes like, I don't know, something that makes better sound, I don't know. Okay, now this is better. It does that, right? This is its, let's say this was the impulse. This is the impulse response. If I hit it 2 minutes later, or 2 seconds later, it should go this like 2 seconds later. If the impulse response is not shifted like this, it means that I hit it now, but it went like this 2 seconds earlier, which is not exactly meaningful as long as you're assuming causality. Right? If the input is shifted, the output needs to shift by the same amount. So if this is the impulse response, if I shift my input by some amount, by tau, the output, even if it's time invariant system, it means that it produces the same output but with the time shift. It has to. Otherwise, it's just like a strange system. At least, I mean, it would be a non-causal system, or which you can have. I mean, mathematically, you can have. Physically, you probably. I mean, we don't know if you can have one or not, but yeah.
So the time invariant assumption is also an assumption of causality?
No. Time invariance assumption, it means that the system doesn't change with time. You can have time varying systems that are causal.
Oh, okay.
Right? Time varying system, you can have all sorts of time varying systems that are causal. It's a system that changes with time, right? I mean, let's say you make, we are time varying systems, right? If you give me a problem this morning, early in the morning, I may behave differently if I compared to if you give me the problem in like 2 in the morning, right? I don't know. It may be different for you guys. But anyway, so, and what is the beauty of impulse response? Why impulse response is interesting? Basically you're hitting the system with this impulse. The impulse is pretty rude, right? I mean, it's the hardest thing you can do to the system. One of the hardest. Well, you can even come up with worse things than impulse. But it's a pretty strong stimulus, right? Why the impulse response? What is the point of using the impulse response? It actually controls behavior and character of the system out. Because it is such a sharp, rude awakening kind of thing, right? Human beings can be, you can think about them as simple systems. They're neither linear nor time invariant. But if you wanted to determine somebody's impulse response, if you want to see somebody's real character, true character, look at them under pressure, right? I mean, everyone behaves normally under regular circumstances and things are nice. If you want to see somebody's true character, put some pressure on them and see how they behave, right? And the impulse is the limit of that. If you want to see the true personality of someone, you can look at their impulse response. Not that I suggest or condone doing that, but what would the impulse response of a person, how do you determine an impulse response? If you had there were no repercussions or no morality or anything like that, so what would you do? What is the impulse response? Say again? Well, death. Okay, so that's an interesting one. Death is the impulse response. Well, okay, it's a
die within 5 minutes.
Yes. Well, convince them. So tell them that they're going to die in 5 minutes. That's one way. Punch them in the face. I don't know. Things of that. Again, as I said, but things of that sort, right? So that brings the true character of somebody. The same thing is true about systems, right? No. It probably says more about you than the person you punch in the face. Yeah. Yes. But nonetheless, the response you get. But generally, you see that people are kind of the interesting characteristic of systems come out under unusual circumstances. So this is the most unusual circumstance, one of the more unusual circumstances, let's say, that a system can experience. And that's why impulse responses are interesting, because what you see later on is that all the natural frequencies of the system come out when you hit it with an impulse. And we haven't talked about natural frequencies, but we'll talk about them. So all of the interesting things come out of that. So anyway, let's quickly see if I haven't missed anything. Now, this impulse decomposition that we had is not the only decomposition you can have for signals. You can express signals in terms of other basis functions, right? And that's the basis for what we call Fourier transform later on. You could describe them in terms of complex exponentials, e to the STs, and that becomes Laplace transform. So you can use different bases and produce different things. But anyway, so this is what we're going to do. So what we're going to do, I guess you have a question, so go ahead.
Yeah. What is little h of tau? I mean, I know it's big H on delta, but what would it look like?
Oh, okay, it depends on the system.
Okay.
It's actually something that this is the interesting thing. This is probably the most important thing, which I should have emphasized more, is that if you have a linear and time invariant system, which for short we call LTI, linear time invariant, and this is an abbreviation we'll use a lot, you can determine the response of the system to any arbitrary input using this. The same thing is true even if you had just linear system, you could use the superposition. But so this is the most important result really, which is y of t is integral of x of tau, h of t minus tau, t minus tau, d tau, from negative infinity to positive infinity. So it allows you to find the response of a system to any arbitrary input x of tau, as long as you know its response to h of t, to the impulse. Or as long as you, so all you need to know for an LTI system is the h of t. If you know h of t, if you know its impulse response, you know everything there is to know about it. You have completely characterized it, and that's all you need to determine its response to any arbitrary input. This is really the generalization of what we did with those like piecewise linear things like half an hour ago, right? So this is the most important result, that you can actually determine the response of a system to any arbitrary, an LTI system, to any arbitrary input using the convolution of the impulse response and the input. Very powerful if you think about it. Okay? Any other questions? So we are going to take a quick break, and then maybe come back, we'll go show you examples. How it works. This is theoretical.